Hi everyone. So I think we should start. We already have people still arriving. So okay, let me start sharing the presentation, and hopefully by the time most of you will be here.
Good day.
Hey. Okay, let us start. So welcome everyone to our first lecture of machine learning course. Officially, if I'm not mistaken, it's called Mathematical Methods of Data Analysis. I'm not sure, but we will be calling it machine learning for simplicity. Yeah, my name is Anna. I will be one of your lecturers, but I'll talk about it a bit later. Before we start, I would like to encourage you to interrupt me whenever you have questions. You can, of course, ask them in chat, and I will be trying to keep an eye on that. So the course is officially supposed to be read in English. So I can't speak Russian. I can speak Russian, but yeah, I'll try to speak slower if that is a problem. But if I forget, let me know.
Excuse me, we have already discussed it with our seminar teacher, but maybe at least some complicated moments, maybe about some mathematical terms. Can you duplicate them in Russian, please, at least? Because there are students who are really poor at English, so for them it will be very, very difficult to understand.
Okay, so if something is not clear, so let me know straight away. So just don't wait till everything becomes super unclear, because sometimes for me it's not clear what is like a difficult mathematical term that should be translated and what is like an obvious term that should not be translated. So as soon as something is not clear in English, let me know. And if you do it with your voice, not in chat, it will be even better, because I may miss the message in the chat straight away and notice it slightly later. So that will be a bit confusing for you probably. So yeah, but I will try to be precise. And I also wanted to mention that in machine learning, there are a lot of terms that not always obvious how to translate in English, in Russian, sorry. There are some translations that people use in Russian community, but overall it's a pretty new field, and most new terms that are being emerged, they appear in English, and it's always better to know the English translation. So if you don't know some terms, I encourage you to learn them during this course. It's a good opportunity, I think.
Yes, we won't need any terms that don't have any translation into Russian.
It's hard to say. So all terms that we will be using, I of course will explain. And if that won't be clear in English, I will translate them into Russian. And if there is no translation, I will also mention that. But just let me know if something isn't clear, okay?
Thanks.
So I also see some questions in the chat that, will the lecture be recorded? Yes, it is recorded, and we will, I think it should be published on YouTube or on Computer Science Department YouTube channel. Is there an opportunity to take grade from another course? No. If you already have taken machine learning course before, it's totally fine that that you won't attend lectures or practicals. There is no, you won't get any, we won't punish you for not attending anything. So the only thing you will have to do is to pass the assignments, to hand in the assignments. And if you already had machine learning course, that might be pretty easy for you. But I will mention the grading scheme in a few slides.
I'm so sorry that, but if we ask you in Russian, can you answer in Russian? Or you will answer at all questions in English?
Yeah, I will be speaking in English during the lecture if I'm talking to the whole class. But if you have a personal question, you can ask it after the lecture in Russian, and I will answer in Russian then. But when I'm talking to everyone, I'm supposed to speak English.
Просто у нас семинарист, как интересно получилось, у нас семинарист даже с нами в Телеграме переписывается на английском.
As far as I know, we discussed that it's okay to talk in Russian during the practicals if all the students are Russian. But all the materials and all the materials and lectures will be in English. But you can talk in Russian with your practical teacher if he or she are okay with that. And again, please don't think that we are trying to make your life harder. It's the other way around. Speaking English, and especially like in the professional community in which you all are, it's pretty important. And being able to express yourself regarding the topics that you're learning in the university in English is also very important. So this is a great opportunity for all of you to practice your English and to improve it if it's not in a high level yet. Okay, so don't, I don't know, don't think that we are like, want to make your life too hard. It's only for your, it will be much better for you. Okay. So we will begin with some logistics, and we already started with that. I didn't know there will be so much questions about the language of the course, but still. So all the materials about the course will be published on this page that you see on the top of the slide. And there you can find all the links that I will be mentioning now, all the materials, etc. The assignments that you will be having, you will hand in any task. And we also have a Telegram chat for all the students and all the teachers. Link is here, but probably most of you will also have separate chats for each group. That's up to a teacher of their practical group. And finally, we will have a Google form for your feedback. For example, if you want to anonymously report something to the course team, or you have some issues and you don't want to write them in Telegram or personally, you can use this Google form to write whatever problems you have. Okay, I see there are like a lot of messages in the chat, but I think they're not for me, so. They're about Evgeny Sokolov mostly. Okay, so this is our course team. So we will be having 2 lecturers, myself and Evgeny Egorov. You will meet him next week. So half lectures will be read by me and another half by him. And we also have 4 class teachers, and I think most of you have already met them. So you know who your class teacher is. I think only Polina didn't have her class yet. So those who have not, those who don't know how their teachers look like, this is their photos, if you're curious. So the general plan for this course will be having 15 lectures and 15 practical sessions, 1 lecture and one session per week. And again, as you've noticed, most practical sessions are 1 week ahead of the lectures, because you already had your first practical session, but this is the first lecture you're having now. Can I share the link to, yeah, I can share. What's happening? Okay. Oops, I sent it to one. No, sorry, it doesn't work.
It's already shared. Thank you.
Okay, thank you guys.
I'm sorry, shall you share the slides with us?
Yeah, as I mentioned, so this is the link on the top. I can send it to Telegram chat after the lecture, and there you will find all the lectures, all the practicals, assignments, etc. Everything will be there. Or you want the slides right now?
No, it's not needed right now.
Okay, then I will publish them as soon as the lecture is over. Yeah, thank you, Alexander, for sharing the link. So the course plan. I'd like to separate 3 groups of topics we will be covering. The first one will be about supervised machine learning. We'll have 7 lectures, not including this one in this group. We'll talk about gradient optimization, linear models for regression and classification, about decision trees, and all the ways how we can make ensembles of models. So this is a so-called classical machine learning, probably, that most people discuss in all the machine learning course. We will also have 2 lectures devoted to unsupervised algorithms, such as clustering, anomaly detection, principal component analysis, or PCA for short, and expectation maximization algorithm. And then we will have 4 lectures, which I call here advanced topics. So it's less conventional topics to discuss during machine learning course. And there we will discuss some Bayesian methods, such as Bayesian linear regression and Gaussian processes. We will also briefly talk about neural networks, because nowadays, well, it's hard to say that you know machine learning if you never heard at least about feed-forward neural networks. So that we will also briefly talk about. And there will be also 1 lecture devoted to deep generative models. This includes such very popular models as GANs, variation autoencoders, basically models which generate different high-dimensional objects such as music, images, text, and so on. And we also will have introductory lecture, which is today, and the summary of everything will be the last lecture. So regarding the grade, as I said, we will have 6 assignments. 5 of them will be compulsory and 1 will be optional. By compulsory, I mean that if you don't do the 6th assignment, the last one, you can still get 10 points for the course. So the formula is, as you can see on the slide, so we take the average grade for the assignments. It will be 70%, and 30% for the grade will be exam. But there is an opportunity to skip the exam if you want. So if your average grade for the assignments is 6 or higher, you can choose not to go to the exam and just get this grade as a final one. So if you manage to do all the assignments perfectly and you get 10 for the assignments, you can say, okay, I don't want to go to the exam. I will take my average grade for the assignments and be happy with that. But of course, you can choose it only before the exam, because you can't decide afterwards whether you want your grade for the exam or not. On the exam, we must answer only in English. I think that's discussable, because the exam will be oral and you will be talking one-to-one with the teachers. And if you will find it really hard to express yourself in English, I think we can do that in Russian.
Excuse me, I think that one optional task is harder than 5 compulsory tasks, yes?
Can you repeat the question?
One optional task is harder than 5 compulsory tasks.
Yeah, so the last assignment, 6th one, will be about the advanced topics. So it will be harder than first 5. But yeah, that will give you an opportunity to get extra points for the assignment.
Okay, thanks.
So that's all I wanted to discuss about logistics of the course. So are there any other questions at this point?
There will be no colloquium on our topics.
And no Kaggle competitions. So
your class teachers are now discussing whether they want to make Kaggle competitions in class, but that will not count towards the final grade.
okay.
Thanks.
Welcome. Regarding the offline lessons, so the lectures will be online definitely till the end of the course. Regarding the practical sessions, if High School of Economics starts working offline and if teachers are willing to do that, then your practical sessions might be offline. The second part of the course discussed in the minor. I have no idea about the minor. I don't know what's discussed there, to be honest. So I found out about these, that some of you are attending the minor last week because other members of the teaching staff mentioned that, but I don't know. What about rounding of grades? Mathematical rules apply. If 6.5 rounds to 7, 6.4 rounds to 6.
5.5 for homework assignments equals 6 of the final grade, right?
Yeah.
May I ask where are the grades stored, like Excel or somewhere else?
Where is what stored?
Grades.
You mean where they are published? Some noise in the background.
Yes, because when we were passing the exam of economics last quarter, we experienced a situation where it turned out that it rounded 6.5 to 6. So that may be a dangerous issue.
Okay, I will keep an eye on that. We will use mathematical laws to round everything.
Thanks.
Okay, seems like we're done with the questions. So at the beginning and at the end of each lecture, we'll be trying to give you the learning outcomes, basically the list of things you're supposed to understand during the lecture. And I really encourage you to carefully look at them afterwards and make sure that you understand and you can answer or describe what's mentioned there. So regarding this lecture, since it's an introductory one, we want you to understand from this lecture what are the goals of this course. We want you to know some key objects that we will be operating during the course and have some understanding how these problems that we will be discussing in the course are connected to real world applications. So to begin with, let's discuss the course goals. They're pretty straightforward. So we'll be talking about some major problems discussed in the data analysis. And today I will mention what kind of problems we're talking about. We want you to recognize, apply, understand the algorithms of machine learning that are used to solve these problems. By recognize, I mean, understand what model is applicable in this or that situation. We also aim at showing you how to work with Python libraries aimed for data analysis. I think some of you already are familiar with them. If not, we hope the course will help you to get fluent in them. And also, a very important step in machine learning that sometimes people forget about is collecting and pre-processing data. And that's something that will be also paid a lot of attention to during the practical sessions, how to properly pre-process and explore the data that you're given or that you're going to collect. So let's start discussing the main concept. What's that? I'm sorry.
В дверь позвонили.
Yeah, I'm sorry, guys. The fire alarm started to ring. I'm trying to figure out how to turn it off. So give me a sec.
А там почти экскурсия получилась.
Могли посмотреть, как живет наш любимый лектор.
Ребят, я тут залип немного. А что произошло?
Алярма.
Короче, алярм
случился и вообще прям...
Кто-нибудь один, пожалуйста.
Пожарная сигнализация сработала.
Прикольно.
Карим.
Это огонь и жопы студентов.
Это кидаем F в чатик.
Это огонь от тех, кто не знает английский.
Огонь. Да, точно.
Да ладно, пока все понятно было.
Конечно. Вообще все ичи.
Что было?
Дмитрий, everything is easy.
Yes,
Hey guys, I'm here in the place where you probably can hear less noise. And I hope I will not die in the
We
fire.
still hear some noise.
I also do.
But it's quite okay.
Okay.
We
So
hope
let's...
nothing will fire.
Yeah, I
No,
also hope
continue
so.
this lecture with fire alarm.
Are you in safety?
Yeah, I think it's a false positive fire alarm.
Look
We're
in the
trying
mirror
to
for
turn
the
it off.
fire.
Okay.
Smoke weeks every day.
So let's continue talking about machine learning, and hopefully the fire alarm will turn itself off. So what is machine learning? Machine learning is a field of study that, and now I'm quoting Arthur Samuel, is a field of study that gives computers the ability to learn without being explicitly programmed. So what does it even mean? So to understand what that means, let's turn to some examples, very simple ones. What if there's a problem to convert hours into minutes? So the problem seems to be pretty straightforward, and we do know the formula, which will help us to find an answer. Basically, if you have some number in hours, to convert it into minutes, you just need to multiply it by 60. Another similar by the complexity problem would be how much time will it take for an object thrown from the height x to reach the ground. So if you were Galileo Galilei, that might be not a trivial question. And we know that he was conducting experiments and collecting data to figure out what would be the time. And yeah, I'm talking about a very abstract and simplified problem, of course. And now we know that given this simplified version, we can just apply the formula to get this time. But let's now talk about a slightly different problem. Assume that I'm showing you a picture of a cat or a dog, and your task is to say who is in this picture. And turns out that it's not trivial to figure out what the formula would be to figure out whether it's a cat in the picture or a dog. Of course, you can define some features of a cat, of a dog, and use them to distinguish the two of them. But depending on the view from which you're looking at this animal, depending on the color of its fur, and depending on the breed, they might be really different. And turns out that for such problems, it's pretty complicated to explicitly write down an algorithm. Another example of such problem is text sentiment, where you're basically supposed to classify a text as either positive or negative. And here on the slide, you can see some examples, and not all of them are obvious how to classify. Namely, if you say that there is a negative word, then you need to check whether there is a negation in the sentence, and so on. And yeah, Andrei, I'm sure I'm safe. That happens. There is somebody who is solving the issue with file arm. I'm not just waiting for it to stop. And yeah, so regarding the sentiment, not only it's complicated to write an algorithm just using an algorithm which will use different words to figure out whether the text is positive or negative, but there is also such thing as sarcasm, which probably most of you are familiar with, and yeah, how to hard code a sarcasm, or how to hard code the model that will be looking for the sarcasm in the text. So this basically brings us to the difference between machine learning and traditional programming. In traditional programming, we usually have an algorithm that was predefined or that we know how to work, and we have the data. We give both of them to our computer program, and that produces an answer. In machine learning, the situation is slightly different. Usually we have data and we have correct answers on this data, or we know how the answer should look like. And we use these two components, we give them to the computer, and we are hoping that the computer will return the proper algorithm. Yeah, fortunately we are safe. I hope you're as happy as I am about it. So if we, for example, return to our example where we've been classifying cats and dogs, we can say that input to our computer will be a set of images and labels for these images, which say whether each image contains a cat or a dog. And given this set of data, set of images and labels, we would like to derive an algorithm which will classify these images. Okay, now I can turn the camera back on. I'm really sorry for this. So yeah. And a very interesting example, which usually is used to show the difference between machine learning and some traditional programming, is difference in two very popular models. The first one was developed in 1985 by IBM, if I'm not mistaken. And it was a program named Deep Blue, which was playing chess. And yeah, it was not developed in 1985, probably it was earlier. But in this year, it basically won the, at that time, best person in the world who was playing chess, Garry Kasparov. And why it was incredible? Because the possible number of moves in chess is more than number of elements in the universe, if I'm not mistaken, which is something about 10 to the power 123, which is pretty a lot. But how this algorithm worked, basically, it was a very smart search tree, which was looking through all combinations and trying to choose the best one. But then in 2016, which was pretty recently, and that's something most of you heard about, I think, is when Google's model AlphaGo won the world champion in Go. And incredible thing about this one was it was not possible at this point to search through all possible combinations because in Go, the number of possible combinations is much higher than in chess. And it's around 10 to the power 360. So what Google was doing in their AlphaGo is exactly looking at all possible games, not all possible, looking at different games played either by people or by the computer itself, and just learning to play as good as these people or programs are. And that was like considered as a revolution, and everyone was super excited and so on. Even though most of the algorithms they were using, they were already known by that time. But why it happened right now? Why in 2016, for example? Because to be honest, methods, as I already mentioned, methods that they were using, they were actually known at that time and much earlier. Even more, most of the algorithms that we'll be talking and discussing in the course, they were developed long time ago. Well, long time ago, I mean in 20th century. But they got popular only pretty recently. And the reason why that happened is the availability of computational resources. And this was supposed to be a GIF, but it's not working. But I can show you the video here, which you've probably seen. Just basically shows you the amount of calculations per second most powerful computer can make. And it was estimated that this number grows, it doubles every 18 months since mid-20th century. And yeah, the only thing that happened recently is that computers became too fast. And now we are able to process and train pretty sophisticated algorithms, which have seen a lot of data. Some more examples, some more fancy examples, I would say. So in 2017, there was an algorithm which learned how to play poker. And everyone was super excited about that, even more than about Go, because, well, this guy can bring you more money. In 2018, the OpenAI guys learned a computer to play Dota, which was even exciting for Bill Gates, who was twittering about it for some time. And not last year already, but in 2019, Google introduced their model, which was playing StarCraft. And this one was even more complicated. And the cyber sportsmen, they were shocked that it's possible to basically be better than they are, that the computer can be better than they are in this game. But of course, games is not the only application. So I suggest, probably most of you seen this, but if not, Algorithm for Civilization, I don't know, but I think it's, if they can't play StarCraft, I think Civilization is also possible, but I haven't seen anyone developing it. So what about this picture? So does anyone have an idea? Yeah, Anton guessed it right. So what does these people have in common is that they do not exist. Exactly. So they are all generated by deep generative models. And by this link, you can go and get even more unreal faces, which look extremely as if they were real. Another pretty exciting application, I would say. I don't know if Genny, if you exist or not. I can't check it. I don't even see your face. Yeah, so another interesting application is protein folding. So this is a very recent one. And this is, again, the model developed by Google, and it claims to solve the protein folding problem, a very popular and very important in biology problem of basically predicting the structure of the protein in the 3D space. I'm not a biologist, so I can't explain how important it is truly, but it's really interesting that it's starting to be not only games and fun, but also a pretty useful applications for humanity in general, probably. Another application which is not about games, but which is still pretty fun is deepfakes. And it started as a fun thing when people were just putting Nicolas Cage face everywhere, and that looks amazing. But yeah, now we're starting to think of whether we can trust all the news and pictures we can see, because it's pretty easy to create a deepfake of almost everything. And as an answer to that, there was a pretty famous competition on Kaggle with awesome prizes where the task was actually to detect deepfakes and create an algorithm which will be able to say whether it's a real image or it was faked. So that brings us to a question, what is artificial intelligence? So that all these applications, they sound pretty interesting, but is it actually an artificial intelligence as most people think about it? And most people think about it as on the right picture. And this kind of intelligence is called a general, while what we are talking about is called weak artificial intelligence. And yeah, here's a misprint. It should be not weak as a part of month, but weak as a slabый in Russian, not strong. Yeah, so, and why it is weak? Because it's only trained to perform one single task. For example, it is supposed to detect an animal on the image and say whether it's a dog or a cat. And sometimes it does it wrong. But if it was trained to do this specific task, it won't be able to help you with any other tasks. And moreover, it of course won't be able to decide to start doing another task. And of course, we're not talking about general artificial intelligence at all. To the depth of my knowledge, we're pretty far from this yet. So the only thing we are working on and we are discussing now is weak artificial intelligence. So that brings us to the end of the first more entertaining part. And now we will be, so Denis said that GPT can solve different text-related tasks. Well, what GPT-3 and other GPT models are doing, they are generating text, right? And that's the task. So you give the beginning of a string, and it's use this beginning to predict what is the most probable continuation of this text. And that's a specific task for the GPT-3. I think there were some research saying that it actually can do, it helps to work with images as well, but I think it requires fine tuning it as well. So here's a very important question: what you mean by the task. So regarding the main definitions, to make my explanations a bit clearer, I'll be using a running example of predicting a house price. That is a pretty popular problem to talk about. There were a few Kaggle competitions, for example, about it. One of them was from Sberbank, another one from some company which I never heard of, which is called Zillow, but probably it's a good one. So basically the task is we would like to learn to predict the price of a house, but we of course don't know the algorithm of how the prices are formed. Instead, we only have a lot of houses and their prices, and we'll look at these prices. We give these houses and their prices to the algorithm, to the computer, and we want to get an algorithm that predicts the price. So the main object we're talking about when we are saying house, predict, and so on. So we have our object or observation, or sometimes we will call it sample. And usually we use X to define it, and this beautiful X to define all space of such objects. So in our example is houses, X small will be one exact house or description of this house, and space of all possible objects will be all houses that we are considering. For example, if your goal or the task that you're solving is to predict prices for houses in Moscow, then X capital will be all houses in Moscow. If your goal is to predict price of house in Russia in general, then again, your space of all object will be all possible houses that exist in Russia. And we have a target variable. That's something we would like to predict. In our case, that's price of a house. And we, of course, have space of all possible. In case of prices, we can say it's all positive real valued numbers. But in other cases, that can may be only an integer, or it can be only 0 and 1, and so on. So we said that X is a description of an object, but what description means? How do we mathematically define that? So usually we will describe each object by a vector or by a set of numbers, each of them being called a feature. So one feature of an object is just a number that somehow characterizes this object. Again, to give an example regarding the house price prediction, the features of the house might be area of this house, number of bedrooms, the district in which it is situated, and so on. The features may be of different types, and we will talk about it a bit later today. If we combine all objects with the target variables, we'll data set. We have n capital, which tells us how many samples or observations our data set has, and all the pairs that we observe. So each pair is one observation. The next object that we will be talking about is an algorithm. An algorithm is basically a function that maps your feature vector into the space of target variables. Or in other words, it predicts the target variable using a vector of features. The most simple example of an algorithm would be a linear model, where you basically take a linear combination of your features and say that this will give you the prediction. Then, for example, here we have a linear model which says that price of the house is approximately 500 plus 100 times the area of the apartment minus 500 times distance to the city center. When we're talking about an algorithm, it's pretty important to distinguish parameters of the model and hyperparameters. And this difference is the following. Parameters is something that we learn about our model from the data. In the example from the previous slide, we were learning these numbers that we use to define a model, that we have 500 plus 100 times the area minus 500. These numbers we somehow learned from the data, and we will discuss how, but they are called parameters of the model. Hyperparameters is something we define a priori, so before training. For example, the set of features that we will be using in our model is something that we decide before we start training the model. And this is called a hyperparameter. Or, for example, you can think of, you can say, okay, I assume that dependency between my target variable and the feature area is not linear, so I will also include as a feature area squared. So basically the power of a feature that you're including, or you can say it might be also cubic, so we'll also include feature area cube. And that's something you need to decide before training. And that's also a hyperparameter. Basically, any external configuration that you determine beforehand is hyperparameters. So something you want to always know is how good your model is. Basically, how far predictions that your model is giving are from the real values of the target. And to define that, we're using loss function. Loss function computes how far your predictions are from the real values for a given object. For example, if your target is a numeric one, it is pretty common to use square distance. The difference between predicted and real one squared. Other option would be to use absolute value, for example. But as you already know, we are dealing with data set mostly, which has not only one observation, but many. And we need somehow to calculate how good or how bad model is on the whole data set. And to do that, we use cost function. So sometimes people mess up loss function and cost function and call both of them loss functions. So be careful with that. So cost function is the measure of how bad the model is on the given data set. And a pretty common way to aggregate losses over the data set is just to average them. And if we use a square difference as a loss, this brings us to a very common cost function, which is called mean squared error. Again, we just compute the square difference for all the objects in the dataset and average them over all the observations. Here, maybe for some of you, it will be useful to get a translation, if you will. So the loss function in Russian is функция потерь, and cost function. Here we have sometimes an ambiguity because sometimes people say функционал качества, which stands for, which doesn't look like the loss or the cost, right? Because that's the opposite thing. It tells you the higher, the better. So here the ambiguity may come. So probably the cost function is minus функционал качества. So be careful with that. But in English, they're all the smaller the better. The loss function, the smaller the loss, the better. And the cost function, the smaller your cost is, the better. So when we have our data set and we define the cost function, our goal would be to train an algorithm. We usually define a priori using hyperparameters. We define a family of models. For example, if we're dealing with a linear model, what we define is our family of models will be a linear combination of features plus some constant, given all possible values of these parameters. So training a model is meaning trying to find the optimal model from this chosen family so that the cost function is as small as possible on a given dataset. So let's try to formalize it on some scheme. to get a general understanding on how the pipeline that we will be working with almost the whole course will look like. So we have three components initially. We have the model, or the family of algorithms that we've defined. We have a cost function, and we have a training data set. We take all these three, we solve an optimization task, and how we do that, we will discuss in details in the next lecture. So we minimize the cost function on a given data set to find parameters of the model. And as an output, we get our trained model. Then we need to test the model. In order to get the proper or a fair evaluation of the model, we need a separate part of the data that was not seen during the training, which is called test data set, to evaluate performance of this model. So we take this unseen part of the data set called test data set. We usually have some metric that we want to calculate about the model. Sometimes it is the same as a cost function, an average difference between the real value and the predicted one, but sometimes it's something different. Sometimes we want something more intuitive. For example, total number of observations for which we predicted almost the correct number up to some small tolerance. So Mikhail's asking, what about setting up the parameters? Mikhail, what do you mean by setting up? So during training, this step here, we are defining optimal parameters from the chosen family of models. Or are you talking about hyperparameters that we need to define a priori? Yeah, each model has parameters, and training a model is basically finding the optimal set of these parameters in terms of cost function on the training data set. So for example, when we use linear model to predict price of the apartment, and we use mean squared error loss, training means optimizing the cost function with respect to parameters of the linear model. So we're basically solving an optimization task, and this gives us optimal values of the parameters in the training phase. As a result, if we take these optimal parameters, plug it into our family of models, we get a specific model. Yeah, if you're talking about hyperparameters, that's the next step of this scheme. So yeah, by far, we assume that we have a predefined model, so we fixed hyperparameters. But in most cases, we don't know what is the optimal set of hyperparameters is. So what we want to be able to select models with different set of hyperparameters. So what has changed in our scheme now is, now as an input, we have a set of models. That is models with different hyperparameters. For example, first one will be the simplest linear model, when you have all the features to the power 1. Area of the apartment, number of bedrooms, and distance to the city center, if you only collected these 3 features. But then you say, okay, but what if we have squared dependency between target and these features? So I can add all these squares to the model. That will be a second configuration or second family of models. In this manner, I can continue creating new features. I can say, okay, what if my feature will be product of an area and number of bedrooms? I don't know why, but maybe that's true. And that will give me a new family of models. So what we want to get, so okay, we can train and find optimal parameters for each family of models, but how then to select the best one? The wrong thing to do would be to test each of them on the test set, calculate the value of the metric and compare them. That would be the wrong thing to do. The correct thing to do would be to have one more part of the data, which is aimed specifically for comparing different models. This dataset is called validation dataset, and the validation, the name of the dataset validation, exactly comes from the fact that is used to validate or to compare different set of hyperparameters, and based on this validation dataset, choose the best one, which will be then sent to testing and used in production or provided to the customer for which you were training the model. So let's go through the whole pipeline one more time. You define a set of models that you think are reasonable with different sets of hyperparameters. For each configuration, you train your model and you get a set of trained model. Now you need to compare them, and for that, you need a validation dataset. And that should be a separate dataset from the training one. You calculate how good your model, each of your models are on the validation dataset, choose the best one in terms of the metric. As a metric, again, you can use either a cost function or it can be something different. And for the best model, you finally calculate the error of the test set and report the result. What if the model we select, I'm reading the question, what if the model we select on the validation dataset performs poorly on the test dataset? Is it possible? Yes, thank you, Maria. That's a good question. That's definitely possible, and it happens. There may be several reasons for that. It may be that your validation dataset is poor. For example, if you select your validation dataset to have like 5 observations, while your test dataset contains a lot of observations, it might be that the model that you chose based on validation dataset does not represent the good model. So it's pretty important to select a good validation dataset. And there are techniques how to do that nicely. For example, there is some thing called cross-validation that we will discuss in the course, which allows us to use basically all the training data as validation in a proper way. But we'll discuss it later. Another situation, so there was one case when such situation may occur. A second situation might be when you encounter so-called distribution shift in your data. Assume that you collected your data set, you trained your model, you spent a year to select a proper model configuration, to train all of them, to compare, and so on. You had a proper validation data set. But during this year, the situation in the world changed dramatically. And now the data that you're supposed to use your model on and to test your model on is totally different. It may happen like, if, for example, if your model somehow connected to the economical data and the economical situation changed dramatically, the pandemic started, it may happen that your training and validation data set are not relevant anymore. And in this situation, unfortunately, the only option would be to start over, to collect the data from scratch, so that you encounter this distribution shift in your model. What is the difference between a validation and test dataset? So validation dataset is used to compare different configurations of the model or different hyperparameters. So you validate your models, you validate a set of models that you selected on the validation dataset. Based on that, you select the best one. And then only one best one is being tested on the test dataset. Why do we need that? Well, we always need some number which tells us how good or how bad the model is. And in order for this number to be fair, you are not allowed to select models based on this dataset. You can also, that's basically mimics the usage of a model in production. So you trained your model, you select all the parameters, and now you would want to know how good it will work in the real world on the data that it has never seen. And test dataset basically mimics this situation. You don't use it during training or choosing the model, only on the very last step. Did I answer your question, Nikita? Okay, I hope so. Yeah, awesome. Okay, so now that we have a general pipeline in our heads, let's discuss different types of tasks that we have in machine learning. We will not cover all of them, but the most popular or the most basic one, I would say. So firstly, I would like to explain the distinction between supervised and unsupervised models. In supervised learning or in supervised models, and in Russian, and again, like here I'm giving the Russian translation because it's totally different from the English one. In Russian, they are called обучение с учителем and обучение без учителя, supervised and unsupervised. In supervised models, we know the correct answers. Basically, when we collect data, we have features for each object, and we have the values of the target variables. As an example, again, we have our houses, we have their descriptions, and we have the prices. And we use both of them to train the algorithm. The question: in what proportion should be these data sets in perfect world? That's, I think, goes to test, validation, and train. So to be honest, yeah, that really depends on the type of task and the amount of data you have. But like the general rule of thumb, the more the better. So the larger your test data set is, the better it covers all possible situations, the more fair evaluation of the model you will have. But you always have this trade-off that you don't want to remove too many data from your training, because otherwise you won't have anything to train on. He asked about proportion. Okay, so I can tell you like 20% goes to test, 20 other goes to validation, and then 60 that are left goes to training. That's a common way to do that, but that's not always possible, to be fair. For example, if you have 100 observations, then we will have problems even to removing 20% or like 40% for validation and test. And in another situation, when you have like millions of observations, you may say, well, even if I take 10% for test, it will be enough because 10% already covers a lot of like most of the cases that I want to test, and so on. So, but yeah, as Evgeny wrote in the chat, 60, 20, 20 is a pretty common way to go. Okay, going back to supervised and unsupervised. In supervised learning, we do have correct answers, as I already said, while in unsupervised learning, we do not have correct answers. We only have descriptions of an object. But in most cases, we have understanding of how the solutions would look like. For example, you can say, okay, I have a set of images, and I know that images have numbers on them. So I assume that there are 10 groups or 10 classes of images in my data set. I don't know for sure because I don't have labels, but I would like to determine 10 groups so that similar image will fall in one group. Well, this is an example of me understanding how the target should look like. And this problem, when you want to group objects, but you don't know exactly group labels for each of them, is called clustering. So let's start with examples of classification tasks. And again, classification is a supervised problem. We need to have labels for each object in the dataset, and these labels should come from a set of k capital numbers. There are different formulations when we can assume that the classes are intercept. When the classes are intercepting, so each object may belong to several classes simultaneously, or when they are not intercepting, or when you have only 2 classes, it is called binary classification, and so on. there is a very cute story regarding this, regarding classification of cats and dogs. And that probably explains why people so often refer to this problem. So in 2006, there was a very popular captcha where you were asked to select cats from the images of cats and dogs. And not like now we have to select cars and bridges, I think, often. At that point, they were cats and dogs. And the cool thing about it was all these cats and dogs, they were coming from, and that were real photos of real animals that were looking for adoptive families. So after looking at the captcha, you were able to go to the website and say that you want to adopt this specific cat and dog. Because of that, the dataset was always updating, and it was pretty hard to break this captcha, because at that point, accuracy of computer classifying cats and dogs on the images was about 60%, which gives a total probability of passing the captcha by the computer low enough. Unfortunately, by 2014, the computer algorithms became smart enough to classify cats and dogs with almost 99% accuracy. And I think now we can do it with better than human do. And unfortunately, by that time, the project with this adopting cats and dogs was closed because the captcha was not usable anymore. Other more real world or useful now examples of classification tasks would be credit scoring, when we need to define whether to give a loan to a specific person or not. Sentiment analysis, which we also discussed today, where we classifying text into different sentiments. It can be positive, negative. Sometimes we need to classify text saying whether it's abusing, whether it gives some abusing message or whether it hurts somebody's feelings. And slightly less obvious type of classification task is image segmentation. In image segmentation, we have an image, and for each pixel, we need to say to which class it belongs. As a result, we, for example, can say pixel-wise, where is a cat, where is a dog, where is the background, and so on. So it's more or less also a classification task, but much higher dimensional, so to say. So you don't need to give one class for the whole image. You need to give class for each pixel that you have on this image. The second, second in the slides, but not second in general, supervised problem or supervised task is regression. And difference from the classification is that now our target variable can be any real number possible. Here again, we can say some examples that we can find in the web of regression tasks. Of course, you can think of any problems with tabular data where you use some economic data to predict another real value, or predicting something about a patient, some medical condition, and so on, which can be numerically evaluated. But here's another examples with more interesting data coming as an input or as a description of an object. For example, we can predict age of a person based on his photo. And again, our object is a set of pixels. Each pixel can be thought of as a feature, and the output will be a real number which says how old the person is. And another example would be detection. You can go through all this link later if you're interested in. In detection, we're basically drawing a bounding box which should surround an object of interest. Usually detection actually is combined with classification. So you need to draw a box around some object and then say from which class this object comes. For example, you may detect animals, then your regression task will predict coordinates of the bounding box which surrounds specific animal, and then classification task will decide what kind of animal is in this bounding box. When it comes to some examples of unsupervised tasks, the one example that I already mentioned would be clustering. And here you may observe some kind of data. Two very toy examples are given here. And in the clustering algorithm, you will say, okay, I assume that my data has two groups or two clusters, and the algorithm is supposed to give you these two clusters. It should say that this part of data set contains objects from the first class, and the second part of space contains objects from the second class. One more example would be anomaly detection. Again, you have some data, and it may happen that some part of this data is anomalous. That is, it contains objects that are not typical for this data set. And in anomaly detection, we're aiming at finding such objects so that we can remove it, for example, from the analysis, and that will help us to get more stable training of the later algorithm on this data. Or we can say, okay, if this anomaly is in test data set, we don't want to trust the predictions of the algorithm on this observation because it's anomalous. It doesn't look as if it comes from the same distribution as the data we were training on. And it's also unsupervised because, of course, we don't have labels which is anomaly and what is not an anomaly. Otherwise, that won't be an anomaly after all. We can also think of a ranking algorithm, ranking problem, where you have a set of objects. It may be output of the search, which usually contains millions of results, which correspond to your query. And your goal would be to properly rank them, to basically say which is the most appropriate for a specific user at a specific moment in time. And it should be the first, and then it goes the less important, even less important, and so on. And of course, we don't know the correct order in most cases. And therefore, it, of course, can be seen as an unsupervised problem. And the final problem that I wanted to mention is dimensionality reduction. And in dimensionality reduction, we want to take a high dimensional object, which is described by many features. And we'd like to map it to a lower dimensional space so that the most of its variance, the most of information that it stores is being preserved. For example, you might have an object which is described by 100 features, and you would like to describe the same object using only 2 features, for example, so that you can plot it on 2D space. But in such manner that objects that were similar in the initial space, for example, if you had images of the same digit but written slightly differently, in the new 2-dimensional space, you want these objects to be still close to each other. And in 2-dimensional space, you probably want them to be close in Euclidean, in terms of Euclidean distance. And this is a problem that is being solved by dimensionality reduction algorithms. Okay, that was a few examples of problem types. Seems like we have 6 minutes left, so I'll try to finish in time. I think there's the last part of the lecture left, which is devoted to feature types. I'm waiting because I think maybe you still have questions about the previous one, but don't see any questions in chat. Okay, let us then turn to this next part. So in this part, I'll be using this one notation where dj will denote possible values of the feature j. So I have an object described by set of features, and what types of features may we have? Let's see. One example would be, and the most obvious one probably, would be numerical feature, which can take any real number. And I will be just giving you a few examples for each type of feature, so that you have an idea of what it can be. And as an example of feature used for regression task, where we predict price of an apartment, numerical feature might be area of this apartment. If we're solving classification task, where we, for example, would like to determine the diagnosis for the patient, the numerical feature describing our patient would be his blood pressure, if the problem is somehow connected with blood pressure, of course. Second type might be a binary feature, which can take only 0, 1. And examples of binary features would be, for an apartment, does it have a gas supply or not? Yes. If yes, then the feature is 1. If no, then 0. And for a patient, did he take the specific pill that you prescribed him, or did he take the specific pill himself without being prescribed to do so? And more general definition of a binary feature would be categorical one. This one can take not 2 values, 0 and 1, but m possible values. Here we define them u1, etc., um. And examples of such feature would be, for example, for an apartment in which specific district of a city that you're considering, or of a country that you're considering, is the apartment situated. And for the patient, it might be which specialist did the patient visit initially. Was it a cardiologist, or did he come to dermatologist first? And that might be a useful feature to consider. The problem with categorical features that we usually are not able to use them straight away in the models because it's not really convenient. For example, they may be, as in case with different types of specialists, it's not obvious how to convert them into numbers. And there are several strategies of how we can do that. And on practicals, you will discuss them in details and practice using different encodings. Here, I will just mention some of them. The first way to go, and the most popular one, would be to use one-hot encoding, when you just create m separate binary features. So you have m categories, and you create a new category for each new feature for each category. For example, you had 3 specialists: cardiologist, dermatologist, and therapist. And it was one categorical feature. What you do, you will create 3 new features. One will stand for cardiologist, second one for dermatologist, and third one for therapist. And for each patient, this feature will be either 0 or 1, depending on whom did he visit. If you want, and of course, you will remove your original categorical feature and leave only these binary ones. You can also use frequency encoding, which will substitute the categorical feature by one numeric one, where you will just encode each category by the frequency with which it appears in the training data set. For example, if half of observations in your training data has category cardiologist, then you just substitute the category cardiologist by the number 0.5, and so on. And the last one is mean target encoding, which also takes into account what is the target value for the observations that have this category in this feature. What we do here, we compute average target within category, and use this mean target as an encoder of a specific category. And again, in more details, this will be discussed during practicals, and you will see how you can properly encode all possible categorical features. And the last feature I wanted to mention, it is an ordinal feature. It's pretty similar to categorical one, with the only distinction that there is some order in the distinct values of your categorical feature. Basically, there is a way how to put your categories in line and say that like this is higher than the previous one, because higher may be in different senses, but As to give an example, which hopefully will help you understand what's going on. Example of ordinal feature may be type of locality in which apartment is located. For example, it can be a very large city, a smaller one, and a village. So here you have, on one hand, a categorical feature. It can take only 3 distinct values. On the other hand, there is an obvious way how these values are ordered. We have a large one, smaller, and even smaller. And the same would be for this medical example, a risk factor for a patient. It may be measured on some scale from 1 to 5, where 1 would be no risk of heart diseases at all, when 5 will be person have very high risk of heart disease. And again, on one hand, this is a categorical feature. It can take only 5 values. On the other hand, it's obvious that they are ordered in some sense. So we have to take that into account when encoding these features. And again, this also, you will practice working with all kinds of these features during practicals. So this brings me to the end of today's lecture. Yeah, I'm slightly over for 2 minutes, I'm sorry. And I also want to again excuse, I would like to say sorry for this situation with fire alarm. Yeah, thank you a lot for your attention. Don't forget to go through the learning objectives one more time and make sure you understand everything. If you have any questions, it's time to ask them. If no, thank you for your attention and see you on the next lecture.
Goodbye.
Thank you for lecture.
Bye. Thank you. Goodbye.
Спасибо большое.
Bye.
You're welcome.
Спасибо вам большое. Хорошего дня вам.
Спасибо.